So the first step is sine x. We have to create the equation that gives us the function. So we are moving everything to the left-hand side, and this is function f of x, which is sine x minus x squared plus 2. I know that this is a function continuous everywhere. I only have to determine a interval, preferably of 1 unit length, that has this function changing its sign. By the intermediate value theorem, if a continuous function on an interval changes its sign, it must cross the x-axis. It must have a solution. Yes, Ricky?
So do we plug in f of x into y?
Correct. We are going to put in the y equals in order to plug in numbers in it. Yes, you don't want to do this by hand. Yes, of course. So this is what we did with all the problems. So in y equals, so let me change because, as you know, it goes back to default. Yes, Brayden?
Don't we find f prime of x and then do x minus?
We can find f prime. However, I still have to find the interval where the solution, at least one solution exists. It doesn't matter. The order is not important. Just make sure that you have the mode in radians. So minus x squared and plus 2. I think the mode is in radians. In my case, yes, it is. Second and table. And I'm going to plug in -1, 0, 1, 2. Okay, I found an interval which is 1, 2. I'm happy with it. So I know a solution by the intermediate value theorem. There exists a c in the interval 1, 2, such that f of c is 0. So such that f of c is 0. So I know there is a solution between 1 and 2. Now we do find f prime, and we get cosine x minus 2x. We create what I like to call Newton's function, which is x minus f of x, which is sine x minus x squared plus 2, over cosine x minus 2x. And we establish an x0. So we either start at 1 or we start at 2. Yes, Ricky, please.
So Newton is x minus f of x over the f.
Correct. That's the formula. We determined it in class together. It should be in your notes. Okay, perfect. So would you like to start with 1 or would you like to start with 2? It's not going to be any problem because cosine 1 radian or 2 radians is not going to be the same with -2 or -4. So there is no problem. The derivative will not be 0 either at 1 or at 2. Neither at 1, neither at 2. So it's not a problem. It doesn't matter. Where do we want to start?
2.
We want to start with 2. That's fine. Perfect. So we go back to the calculator. So we go to variables, y variable, call the function y1, press enter. I forgot to get out of that window, sorry. Okay, variables, y variable, y equals 1, y1, in parentheses, we decided to start with 2, that's fine. We start with 2, and now I copy second and entry and overwrite 2 by the previous answer. And now I do this repeatedly. Enter, second and entry, enter, second and entry, enter. Okay, now it doesn't appear that it's converging anywhere. So there may be a mistake somewhere. So I have to go back and look, right? I'm expecting a solution between 1 and 2. Remember, there are two possible problems. One, the derivative is 0 for the x0 that we pick. The other one, there is a max or a min between 2 and the solution. So I may have to go back and reassess and start with 1. But first, I want to check my Okay, got it. X minus, parentheses. Disregard what I just said. I mean, what I just performed. I went ahead and did not put Newton in there. Wonderful. However, what is important is to identify that something is wrong and go back and reassess. That's more important than anything. And minus 2x. I knew that something was wrong. Perfect. So now don't forget to get out of there, clear everything. So we want to call y. And we want to call y1. We want to start with 2. We started with 2. We got whatever. Yes, that's more like it. Second and entry and overwrite the previous answer. And now you're on the right track. Now we only have to establish how many decimals we want. And then we'll stop based on where we want to stop. I think that this is more than enough. So as you see, 72 and then 728466, 728466. I'm happy with 6 decimal places. So the solution is 1.728466. I'm happy with that. Yes, Ricky? Yes, cosine x minus 2x. Close the parenthesis for cosine. No, you have to close the parenthesis for cosine. Right there. Yes. Okay, minus 2x. And now close the parenthesis for the denominator. And now second and quit. And now we go to variables. Y variables. And we want a function. And we want function y1. And we put in parentheses 2. Close the parenthesis and press enter. And now we want second and entry. And we go back and override 2 with second and answer. That's it. And now press enter. So now this new answer uses this inside. Now go to second and entry again. Now you don't have to do anything, just press enter. Because now it uses this answer inside. And now it uses this answer inside. And you're more than... Yes.
I got an error when I retyped in error syntax.
Let's take a look.
I think I didn't do parentheses right in my line.
So here you don't need a parenthesis for that. You don't need a parenthesis for this. Okay, that is good. You don't need a parenthesis here. And now you're fine. So variables, function, y1, in parentheses 2, press enter. Now second and entry, and you override it, yes. And then you just copy this and as many times as you want. Thank you. Okay, are we okay now with Newton's method? Everyone?
Yeah.
Yes? Is Newton's method clear now? Yes, everyone? Okay, very good. Next question. Is there anything else?
So is that the final answer?
That's 6 decimal places. 1.728466. Yes. There may be more than one solution. I don't care. I only want you to determine one. 1.728466. But remember, you have to list. You have to list the iterations that you get, not just the last number. So you do have to list x1. You have to list x2 and say this is my x3 and it's done. Depending on how many decimal digits we agree upon. Is this okay? Yes, Ricky?
Just stop
When 6 digits repeat.
okay.
So in the previous example with the calculator, as you see, I had, we started with 2. So that was x1. This is x2. All you need is x3. You don't need x4 because the 4 digits already repeat. So the method converges in 3 steps. This is x1, this is x2, and this is the solution with 6 decimal places. You don't have to write the next one because all these 6 digits repeat themselves already. Good. Anything else? Anything else, anyone? Anything else? So are we okay? Are we ready for this test on Saturday? I also increased, as I said, the number of points on the bonus. So your test will be in the testing center for 3 hours. You need an hour and a half for everything, but I will put it in for 3 hours. You're taking the test here on Saturday or in the testing center before Saturday? Before Saturday. Okay, 3 hours. Because there is also bonus. You don't have to. So if you don't want the bonus, you don't have to do it. But it will be there, okay? Okay, very good. Other questions for me? Other questions?
Yeah, I have a good question.
Yes?
So how do you put like variable and y1 on top?
It's already in there. Once you put it in y equals, it's already in there.
I was trying to do it.
Once you put y1 in there, you already have y1. You put that parentheses around the denominator. So you remember, if you don't put parentheses around the denominator, you're not going to get it. So parentheses around the numerator and parentheses around the denominator.
Thank you.
So you don't need the table. So we go to variables, y variable, it's calling y function y1, then we put 2 in it. And then you go to second and entry, it copies the entry, but now I want to remove the 2 but put this in. So it's second and answer.
Oh, okay.
So now every time we press second and answer and enter, second and answer and enter, it will always put in the previous number. If you type it in, you will truncate the answer and approximate it. So that's why you want the calculator to do it automatically. Okay. So let me see. It's okay. That's fine so far. That's fine so far. Perfect. Just this one doesn't, you don't need it. So now you go to second and out of nowhere. So now you press variable. Go to y variable and press y1. And new parentheses and press 2. So we get our x1. But now with second and entry, you go back and change the answer. So now I want in y1 this number to be plugged in and press enter. And then second and entry, enter again. Second and entry, enter again. You will always use this previous answer and put it in the function. This previous answer and put it in the function. Yes.
So when you go to y1, you gotta press enter.
Yeah.
Then I press enter.
But not there, in the viewing window, right here. So in second and quit. So you want the variables, you go to then you click this, and now you put 2 in parentheses. Not in y equals. This is not in y equals. This is in the main viewing window. Yes, repeat. Yes. Yeah, it's the same thing. It's the same problem. Everything is. I want to show you how. Yeah, exactly. I know. But you have to find the interval because you have to find and you have to start with something. If you don't find the interval, you understand why we find the interval. You understand? So now we know the solution is between 1 and 2. That's why we have to solve it at 0 equals 1. If I don't find it,
So you have
You have to be able to
if I don't find an interval, then I will not.
Yeah, because you were in here and you were in your equation and you just deleted the
So
one
that's
that you
what
were
I need
adding
to
back in. That's why you weren't doing it.
Okay, anything else? Is this clear now? Every step? We can, after class, if you would like to sit down with me, I'll be more than happy to show you again if you still have doubts about the method. We can do it again or on a different problem. Is that okay? Me? Okay, so let's continue. So if you remember, we said that the exact area, ready? The exact area was limit as n approaches infinity from the sum from I equals 1 through n from delta x f of xi. Correct? Okay, so this is the exact. Absolutely no approximation here. This is the exact number. Here's another way of determining the area under the graph of a function between 2 points. What letter is this?
Sigma.
Yes, it is sigma. It's the Greek letter S. So this is how we write that letter, correct? We're going to extend it, and we're going to write it like this. It's still a sum. This is still a sum. It's still S, but a long S. Ready? So this interval that we are looking at was the interval a comma b. So this is the area, the exact area under the function f of x on the interval a comma b of the limit of the Riemann sum. Yes. Any questions? Yes, Ricky.
5.1.
It's 5.3.
5.3.
So this is the integral. To be exact, there are two different types of integrals. This is the definite integral from a to b. What do you think I'm going to write in here? Just look at what you see here and say, it's the sum. What are we adding up? Areas of rectangles, right? Indeed. This is the height, and this is the width. One more time, how do we read this? The definite integral of f of x between a and b. Of course, a is considered the lower limit. What is b considered? Upper limit. These two are identical. They're not determined in the same way, but they will give the same thing. And they are identical in the final answer. And the final answer will be a number. Okay? So the integral from a to b from f of x dx is a number. So two types of integrals. One is the one that we just discussed. We don't know how to evaluate it yet. We don't know anything about it. We just know its name. One is the definite, which gives us a number. And the other one is called indefinite, which will look like this. It doesn't have an interval. And it will give us a function. To be exact, a family of functions. But a function for now. So one more time, let's summarize. The area under the graph of a function between a and b can be determined in two ways. With the limit of the sum of base times height plus base times height plus base times height, the area, or the definite integral from a to b from still base times height plus base times height plus base times height, but we use this symbol. This is the definite integral of f of x between a and b. It's still the area under the graph of f of x between a and b. It's a definite integral. It will always give us a number. There are two types of integrals that we will see. One is called definite, which will always give us a number, and the other one is an indefinite, which will always have an answer, a function, or a family of functions. Now, a few minutes ago, when we looked at the previous lecture, we found that there are several properties of the summation notation. What were those properties that we looked at? Basically two, or if you want, you can say three, but yes.
If it's the sum of two functions.
Two general terms, I can separate it if it's a sum or difference. And the second one, or if you want the third one, is the constant goes in front. Of course. Now we're going to have properties of the definite integral. So let's talk about properties of the definite integral, and then we will learn how to determine definite integrals, how to find them. So properties of the definite integral. There are several properties. So here's one. Here's our function. This is f of x. This is a. This is b. Let's say we have a c in the middle. Here's property number one. If the function is a positive function, what do you think the integral from a to b from f of x dx would be? Because areas can be negative. So if the function is positive like this one, all on the interval a comma b is above the x-axis, then this area, which is the integral from a to b from f of x dx, must be a number greater than or equal to 0. I hope you agree. Property number two. Can I write the integral from a to b from f of x dx as the integral from a to c from f of x dx plus the integral from c to b from f of x dx? Would you agree? What I'm saying to you is it clear that this entire area can be written as the sum of two areas, this and this? So the integral from a to b is the same with the integral from a to c plus the integral from c to b. Agreed? Good. Number three, the integral from a to a from f of x dx. What do you think this equals to? Say it again. Careful. Exactly. There is no area. There is no width. If there is no width of the interval, the area is 0. F of x can be whatever you want, but if you have to multiply it by 0, it's still 0. Excellent. Number four, the integral from a to b from f of x plus g of x dx, or minus. What do you think this will be? And you can say, show me a figure, and I can.
Integral
Yes? From a to b?
f of x.
Yes, the integral from a to b from f of x dx. Notice that there is no integral without the function and dx. Okay, and then plus or eventually minus
Integral
from a to b from g of x dx. Thank you very much. Awesome, indeed. Here's the next property. Property number 5. Everything is common sense. Yes, sure. Go ahead.
number three.
Say it again.
Number three.
You have a question on number 3?
No, I just didn't see it.
Oh, okay. Now the integral from a constant from a to b from a constant f of x dx. All common sense so far, right? Okay. What would you say this equals to? Of course. Times the integral from a to b from f of x dx. Awesome. 6. The integral from a to b from a constant dx. Yes, it's c. The integral from a to b from dx. Let's draw a picture of this before we continue. I don't want to just put the answer there. So let's take a look. So the function is a constant. Let's say this is f of x equals the constant. And this is our a and this is our b, and we want to determine this area. What do you think this will equal to? Can anyone give us the area of this rectangle? C times a minus b. Of course, b minus a, I'm sorry. C times b minus a. Property number 7. I'm going to graph a function and you'll tell me what type of function this is. Awesome. It is cubic or x cubed. Very good. Awesome. What type of function is a x cubed or cubic function, polynomial? We know something very important about it.
No reflection.
It's symmetric with respect to the origin, so it's an odd function. Good. So this is negative a, and this is a. I would like us to determine the area between negative a to a from f of x dx for any odd function. Odd function and symmetric interval. Symmetric around the origin, of course. Negative a. Like the integral from negative 5 to 5 from x cubed dx. What do you think the answer would be? Just a wild guess.
2a.
Why? They are identical, but one of them is negative and one of them is positive. Identical areas, one negative, one positive. Yes, 5 with negative 5, right. So this area and this area are identical in size, but one is positive and the other one is negative. So two conditions have to be fulfilled. Condition number 1, or A, odd function. If the function is not odd, the answer is not 0. The second condition, condition B, is symmetric interval. If these two conditions are not fulfilled, the answer is not 0. So odd function and symmetric interval. Property number 8. And I'm sure you're asking yourselves, is there end to this? Yes. There are about 4 more. Okay, here's a function. Can anyone give us the function that I'm graphing? Very good. What type of function is x squared? It's an even function, symmetric with respect to the y-axis. Again, I'm going to write a negative a and a positive a. And I want the integral from negative a to a from f of x dx. Two conditions have to be fulfilled: even function and symmetric interval. What do you think? A wild guess. What do you think the answer would be? 2, the integral from 0 to a from f of x dx. So if the function is even, we do not have to integrate between negative a and a, which is way more difficult than integrating from 0 to a. But we know it's twice that area. They're identical, but they're not opposite. They're both positive. So the integral from negative a to a, if the function is even and if the interval is symmetric, is twice the area between 0 and a. So two conditions here. Condition, one more time, condition A, even function. And condition B, symmetric interval. If the function is not even and the interval is not symmetric, the answer will not be twice the integral from 0 to a from f of x dx. Questions? Questions on this? Everyone? Number 9. I have two functions now. This is f of x, and let's say this is g of x. The interval is still a comma b. This is the area under g of x, and this is the area under f of x. Purple and green. Would you agree if I write that f of x is greater than or equal to g of x on the interval a comma b? Then what would you say about the integral from a to b from f of x dx and the integral from g of x dx from a to b? What will be the relationship between these two? So if the relationship is that f is above g on the interval 0, a to b, then what is the relationship between the green area and the purple area?
Green area is less.
Yes, very good. So the purple area, so the symbol stays. If the function is above a function is above another function, then the area under the first one must be bigger than the area under the second one. And it makes sense. Would you agree? Okay, one more. So let's say this is M. Let's say this is M. This is the interval a comma b. And our function is somewhere here. Would you agree if I write that f of x is between little m and uppercase M on the interval a comma b? I don't know what happens outside of the interval a comma b, and I'm only interested in this action between a and b. Would you agree with this? That f of x is definitely greater than m and less than uppercase M anywhere between a and b? Would you agree? Yes? Then the integral from m dx, the integral from f of x dx, and the integral from uppercase M of x, m dx, of course from a to b, from a to b, from a to b, they have to fulfill this relationship as well. So if the function is in between, obviously this area is smaller than this area, which is smaller than this area. Acceptable? Yes? Well, there are two, I'm just checking the time. There are two that we can determine. The middle one is definitely the integral from a to b from f of x dx, but the sides, we learned a minute ago what they mean. And the property that we used was this. The property that I'm referring to is that one. So what will you say on the left-hand side? What do I have to write? Times? Very good. And what about this side? B minus A. Very good. Okay, so knowing all this, we can look at some applications. Okay, I would like to look at on page 384. I would like us to practice with 47 through 50 for now. On page 384. Write as a single integral in the form the integral from a to b from f of x dx, and this is problem 47. They are giving us the integral from -2 to 2 from f of x dx, and they say plus the integral from 2 to 5 from f of x dx minus the integral from -2 to -1 from f of x dx. They want us to condense. So let's draw a little picture here so I can easier explain what's happening. So obviously the first integral represents the area between -2 and 2. So this is the function. So the first integral is this. The integral from -2 to 2 from f of x dx. We agree? Very good. Let's see what the second one represents. The second one represents this area. So this is our function f of x. So this is the first piece, this is the second piece. But this is from -2 to -1, which is this area that they want us to subtract. So then what is left? And how do I write the final answer?
Is it
Yes?
-1 to 5?
-1 to 5 from f of x dx. Do we agree with this?
Yes.
So we had the green plus the purple, but minus the red. So now the integral is between -1 and 5 from f of x dx. Acceptable, everyone? Any questions on this? Yes, Ricky?
How did you get 5
You mean the limits of integration?
Yeah.
Okay, so the first one is the green territory. The second one is the purple territory. So now I have the integral from -2 to 5 from f of x dx. But I have a minus in front, minus the red area. So I have to subtract that. So that's why I have the integral from -1 to 5 from f of x dx. Better? Yes? Everyone? Yes? Is this okay? Okay, perfect. Let's continue with 48. We are given the integral from 1 to 5 from f of x dx, which is 12. Then they say the integral from 4 to 5 of f of x dx equals 3.6. Find the integral from 1 through 4 from f of x dx. Find the integral from 1 to 4 from f of x dx. So this is 48. From 1 through 5 from f of x dx is 12. From 4 to 5, they say is 3.6. Find the integral from 1 to 4. Any ideas?
12 minus 3.6.
Right, so because we have from 1 to 5, we have from 4 to 5, so maybe it's better if we just present 1, 4, and 5. From 1 through 5, the area, this area, is 12. From 4 to 5, this area is 3.6. So the integral from 1 to 4 is the remaining. 1 to 5 is till here, sorry. This is all 12. The green is 12, from 1 to 5. And then we have the red, which is from 4 to 5, all this. From 4 to 5, assuming that this is 4. Good. So this is indeed 12 minus 3.6. What do we get? 8.4 indeed. Okay, let's also look at 49. Any questions for me? In 49, we are given the integral from 0 to 9 from f of x dx is 37. They're also giving us the integral from 0 to 9 from g of x dx, which they say is 16. And now they're asking us to find the integral from 0 to 9 from 2 f of x plus 3 g of x dx. Again, applying the same properties over and over. Any questions and any ideas? And now we're going to learn how to calculate the definite integrals. Yes, Ricky?
2 times 30.
So this will be exactly 2, the integral from 0 to 9. Yes? from f of x dx plus
3.
3, the integral from 0 to 9 from g of x dx. Good. So I do have this piece that was given to us as being 37 plus 3 times. This is given to us as being 16. And when you have the number, give it to me. Ready? We have a number? 122. There are other properties that we will go back and practice, but right now I would like to move on to the fundamental theorem of calculus. Okay, the fundamental theorem of calculus has two parts. In one part, I'm going to put this in writing in a minute. One part is teaching us how to calculate definite integrals, is showing us how to determine them. The second part shows that differentiation and integration are inverse operations. Can you give me two examples of two functions that are inverses of each other?
The square root, the square
X
root.
squared.
The square, excellent. Exponential and log. Cube root and power 3. Anything else? Addition and subtraction are inverse operations of the same number, right? Adding 5, subtracting 5. Good. Integration and differentiation are inverse operations. So we're going to start with part 2. So there are two parts. Let's write down those two parts, and then we'll start with part 2. So 2 parts. Part 1 shows that integration and differentiation are inverse operations. And we will illustrate that. And number 2, we will start with part 2. It teaches us how to calculate. Yes, Ricky?
So the previous section is
5.1 and 5.2 together, actually. They deal with the same thing. So part 2 shows us how to calculate a definite integral. How to calculate a definite integral. We start with part 2. If a function is continuous on the interval a comma b, then the integral from a to b from f of x dx will be calculated determining, anyone remembers what this is called? Yes, Ricky? The antiderivative of f of x calculated from a to b, which really means we plug in the upper limit, f of b, minus when we plug in the lower limit. And we are going to practice this on as many functions as we can. So part 2 of the fundamental theorem of calculus says this. If a function is continuous, if it's not continuous, you have to wait till Calc 2 when we present improper integrals. So here the function must be continuous on the interval a comma b. if the function is continuous on the interval a comma b, the integral from a to b from f of x dx will be determined by finding the most general antiderivative, as we know from 4.9, and then evaluating, calculating the difference between when we plug in b and minus the difference when we plug in a. And let's start by looking at several examples. And let's see what we get. Yes? Yes?
Can you